this video I explained the design of reinforcement in the secondary y direction long span. So we are talking about this long span where you can see this red one, that reinforcement that we like to provide it. This reinforcement, what is the spacing and what's the area of that reinforcement, red one. We already calculate the reinforcement in the x directions, which is the short span, and that is the primary reinforcement that I saw here in the blue color. These are the longer span, they are secondary reinforcement in the y directions. Now the x is a shorter span, so it's not your horizontal, and y axis x generally the classify as a short span and the y classify as a longer span. I also draw these cross sections. When I'm looking from this side, I can see this bar, red one, that is the secondary reinforcement, and these are the primary reinforcement, blue one. Primary reinforcement generally provided at the bottom surface. The first is primary, and then the second layer comes as a secondary reinforcement. So this is the primary one, which is the blue one, which I can show it to you here, which I can see it when I see it here, and these red bars that are dots when I see it from here, that is secondary bar. When I'm going to look from this side, I would see these dot that are my primary reinforcement, that are blue one along the short spans, and then you have these reinforcement, these are the secondary reinforcement. Now the calculations here, if you want to calculate your dy, I think if you remember that dx we calculated in the previous video. Now we like to calculate dy, and dy we are just getting the reinforcement from the center, from the red to the top. Now we know that from this primary reinforcement we have 119 that we calculated in the previous video. So what is this dy? Dy would be 119. Take away these 6 millimeters because there is a half here, and there is another 6 millimeter for this reinforcement, so total 12 millimeters. So that you have dy 107 millimeters. So in the y direction, reinforcement steel is laid inside the reinforcing steel in the x direction. As I mentioned, we are putting inside of that x direction, and therefore the effective depth from the extreme compression fiber to the center of the steel is taken as 107 millimeters. Now we need to calculate a design moment. I think we done the calculation of design moment in the previous video, where we calculate this my value, mx value. I can show it to you here. In the previous videos we calculated this design moment, that is for the mx. Now we need to exactly the same thing, but we need to calculate the my. Now there is a clause that we're going to use to calculate the my. That clause is shown here. That clause is clause 6.10.3, which is structure analysis, where you have a design bending moments. In here we have my, which is beta y fd lx square. Please note we always multiply with lx, they regardless of, but only the difference is your beta y. How can you find that beta y? If you turn the page over, and there is a table 6.10.3.2a, where you have a two adjacent edge discontinuous. I think if you remember our questions, in our questions we are working on these slabs where we have two adjacent edges are discontinuous. So in that case we are working on the condition 6. On that condition 6, you don't need to calculate ly on lx, unlike you done it for beta x. You can straight away take this 0.035 value as a beta y. fd, I think we calculated this fd in the previous video. I can show it to you here. That was just load factors. We calculated this length LOX 5.150 in the previous video. Please check out the previous video for the detailed calculations. So if you have all the recipe, so beta y I substitute. Where this equation is coming from? That equation is coming from this clause, which is 6.10.3.2, where you will have this my value, beta y times 9.6, 5.15 square. So it gives me 8.9 kilonewton meters. I already discussed this table. Now we like to calculate the secondary reinforcement. Let's say at the midspan, we calculate the moment at midspans. Now what is the reinforcement at the midspan for this 8.9? I think we done previously those calculation as well. I can show it to you. If you remember these discussions, that we have these detailed discussions about these equations, where we have calculated this primary reinforcement for the given moments. Now we have a couple of difference. Instead of 14, we have 8.9 at the midspan. Okay, we done the midspan calculation. So instead of 14, we're going to take 8.9. we have on second difference, small d, we have 119, but we will take it 107. We just calculated that 107 here. So we're going to take 107. So only two difference. So we can use exactly the same equations. Please check the previous video where we discuss the detailed discussion how we derive these equations. So I just copied this 0.85, 500 AS we need to calculate 0.85. Instead of 119, I put 107 D because that is dy, and that moment at the midspan my is put it here. So our reinforcement at the midspan is 230 millimeter square per meter. Now for interior beams, where I'm talking about interior beams, at this particular interior beams where you have a continuous edge. For that continuous edge, I think if you come here where you have this negative design moment, here there was a positive design moment, right? At the midspan you have positive design moment. Here we have negative moment region, so we just need to multiply 1.33 with the midspan value when you use this table. So 1.33, you just multiply 1.33 at the midspan moment, so it's give me 11.8 kilonewton meter. So we can use same equations here, and instead of 8.9 we will use 1.8, and that reinforcements gives me 308 millimeter square per meter. That is at continuous edge. That continuous edge meaning that we at this particular edge. Now we're going to look at this edge again. It is a discontinuous edge and it is a support. We spandrel beams, the support beam, the discontinuous beam is called spandrel beams. And my value, if you turn the page over, they are talking about, it says that negative design moment, it says that for discontinuous edge, it says that you need to multiply by 0.5 when you use these tables. So we just multiply by 0.5 with this midspan moment. So that's, we just multiply. Now we're going to use exactly the same equations, but instead of 11.8 we're going to put 4.5, so I get AS value 119 millimeter square per meter. So what I have just calculated, I can summarize. We calculated the steel reinforcement here 116 millimeter square per meter. At the midspans we calculate the midspan 230 millimeter square per meter. At this continuous edge we calculated this one as continuous edge, we calculated 305 millimeter square. I think in the primary directions we have taken these in the very details, but I have just quickly showed this one here because we are just taking the same approach. In the next video we're going to do this minimum reinforced requirement and CAC control reinforcement and the minimum spacing that we done for X directions. We're going to repeat that one for Y directions as well. So in the next video we will do this reinforcement, whether they are enough for the AS36 requirement. Thank you.